11.16. An electron and a photon each have a wavelength of 1 nanometer. Find A, their momenta, B, the energy of the photon, and C, the kinetic energy of electron. Now wavelength lambda that is given to you 1 nanometer, that is 10 raised to minus 9 meter. H always given to you. Now first we have to calculate the momenta of electron and photon. Here wavelength that is same one for both. Now for momentum we have the equation P equal to h by lambda. Now lambda that is same one for electron and photon. It implies that momentum that will be also same one. H by lambda, substitute the value of h 6.63 into 10 raised to minus 34 upon 10 raised to minus 9, that is lambda, and solve it, you will get the momentum. Okay. Then we have to calculate energy of a photon. Now energy of a photon that is hc by lambda. So substitute the value of h, then c and lambda and solve it. You will get the answer in terms of joule. Then divide it by 1.6 into 10 raised to minus 19. Your answer will be in electron volt. Okay. Then after, kinetic energy of electron, that is p square by 2m. Okay. So that is p we already calculated. Then substitute the value of p and take square of it upon 2m. So here mass of electron. Again you will get answer in terms of joule. Then divide it by 1.6 into 10 raised to minus 19. Your answer will be in terms of electron volt. Clear? 11.17. A. For what kinetic energy of a neutron will the associated the Broglie wavelength be? 1.4 into 10 raised to minus 10 meter. B. Also find the Broglie wavelength of a neutron in thermal equilibrium with matter having an average kinetic energy of 3 by 2 kT at 300 Kelvin. Now lambda given to you, that is 1.4 into 10 raised to minus 10 meter. Mass of neutron, that is 1.66 into 10 raised to minus 27 kilogram. K, the Boltzmann constant, always given to you. Now first we have to calculate the energy for which lambda is this one, means equation of energy, that is h square upon 2m lambda square. Now substitute the values of h, then mass of neutron, and then lambda. Then solve it, you will get the answer. Then after, also find the Broglie wavelength of the neutron, right, in thermal equilibrium. So in thermal equilibrium, the average kinetic energy, that is 3 by 2 kT. So 3 by 2, substitute the value of K, temperature given to you, that is 300. Okay. So you will get energy. Once you get energy, then after, we have the equation for lambda in terms of energy, that is h upon under root 2me. So substitute the value of h, then mass of neutron, and energy which we calculated here. Okay. And then after solve it, you will get the Broglie wavelength associated with it. Clear to all of you? Then 11.18. So that the wavelength of electromagnetic radiation is equal to the Broglie wavelength of its quantum or photon. Very simple thing. See, we have lambda, that is c by nu that is the frequency, or you can write c by f, multiply and divide by h, so hc by h nu. Then we can rewrite this equation as h upon h nu by c, but h nu by c, that is momentum. So we can write lambda, that is h upon, replace this h nu by c by p. So lambda equal to h by p, and that is the Broglie wavelength. Simple thing. Clear? 11.19. What is the Broglie wavelength of a nitrogen molecule in air at 300 Kelvin temperature? Assume that the molecule is moving with the root mean square speed of molecules at this temperature. Atomic mass of nitrogen, that is 14.0076 U. Okay. Now see, K Boltzmann constant, that is always given to you, temperature that you have to take 300 Kelvin. Now nitrogen, that is diatomic. It implies that mass of N2 molecule, that is 2 into mass of nitrogen atom. Atomic mass that is given to you. So 2 into 14.0076 AMU, multiply it by 1.66 into 10 raised to minus 27. You will get mass of nitrogen molecule in terms of kilogram. Now, RMS speed at temperature T, that is V equal to under root 3 kT by M. In standard 11th, we studied this thing. So here now substitute the value of Boltzmann constant K, temperature T 300, and this mass of nitrogen molecule calculated here. Then solve it, you will get RMS speed. Once we get RMS speed, then after we can calculate lambda, because lambda, that is H by P, but P, that is MV. So substitute the value of H, then mass of nitrogen molecule, then RMS speed, which we already calculated, and then solve it. You will get the answer. Clear to all of you? A. Estimate the speed with which electrons emitted from a heated emitter of an evacuated tube impinging on the collector maintained at a potential difference of 500 volt with respect to the emitter. Ignore the small initial speeds of the electrons. The specific charge of the electron, it implies its E by M is given to be 1.76 into 10 raised to 11 coulomb per kilogram. B. Use the same formula you employ in A to obtain electron speed for the collector potential of 10 MV. Do you see what is wrong? In what way is the formula to be modified? Now see, first answer of A, the potential difference at the collector, that is 500 volt. So V 500 volt, E by M, that is given to you 1.76 into 10 raised to 11 coulomb per kilogram. When electron is accelerated under the effect of the potential difference of V volt, the energy gained by it, that is kinetic energy, and that is equal to EV. So we can write half mv square, that is EV. So V square equal to 2 EV by M. So V equal to under root E by M into 2V. E by M, that is given to you 2, and voltage, that is 500. Take square root of it. You will get the speed of electron. Okay. Now suppose we take the potential difference, that is of the order of 10 MV, means 10 raised to 7 volt. Again, if we calculate the speed of electron using the same equation under root E by M into 2E, then here substitute E by M, 2 as it is. Now V, that is 10 raised to 7 volt, and then take square root of it. You will get the answer 1.87 into 10 raised to 9 meter per second. So what is wrong here? So wrong thing is this one, speed that comes to greater than speed of light, which is never possible. Okay. Now, in what way is the formula to be modified? So now we have to modify the formula like this. See, here we have to consider the relativistic mass of the electron. So in theory of relativity, the mass of the electron, that is given by m equal to m0 upon under root 1 minus v square by c square, where m0, that is the raised mass of electron. Raised mass, it implies that the mass of the particle when its speed, that is 0, and when it is moving with speed v, which is of the order of speed of light, then the mass that is given by this particular equation. Now, if we calculate the energy by the equation given in the theory of relativity, E equal to mc square, then substitute m, that is equal to this m0 upon under root 1 minus v square by c square. Then under root 1 minus v square by c square, that is m0 c square upon E. Now, electron is under the effect of the potential difference of 10 MV. So energy gained by it will be 10 MeV, and m0 into c square that we have to calculate separately here directly. The answer is substituted for m0 c square. And finally you will get under root 1 minus v square upon c square, that is 0.051. Take square on both the side, and then after make v as a subject, right? So it comes to 0.999 C. Clear? So here your V that is less than C. So always you have to be careful, the speed of any particle never be greater than C. Clear to all of you? So in this way we have to modify equation. 11.21. A monoenergetic electron beam with electron speed of 5.2 into 10 raised to 6 meter per second is subject to a magnetic field of 1.3 into 10 raised to minus 4 Tesla, normal to the beam velocity. What is the radius of the circle traced by the beam? Given E by m for electron equals 1.76 into 10 raised to 11 coulomb per kilogram. B. Is the formula you employ in A valid for calculating radius of the path of a 20 MeV electron beam? If not, in what way is it modified? So simple thing. See, speed that is given to you, the magnetic field that is also given to you, and E by m that is given to you. Now we know this thing, when any charged particle is moving in the magnetic field B with velocity v, it will execute the circular motion. Okay, and the required centripetal force that will be provided by the magnetic force acting on that particle. So magnetic force, that is BQV, here the electron is the particle, so we can write BeV. That will provide the required centripetal mv square by r. So we can write r equal to mv upon be. We can rewrite this equation as v upon be by m. Substitute the value of v, b and E by m given to you, then solve it, you will get the radius of the circular path. Then after, see, we already discussed this thing. If the electron that is with energy 20 MeV, in the previous example we discussed, it was with energy 10 MeV, then also its speed was greater than C. So here also the energy, which one is tremendous large one, so we can't employ this particular equation. But now we have to modify this one with the help of relativistic mass of electron. So we have to use m equal to m0 upon under root 1 minus v square by c square. So in our equation, r equal to v upon b into E by m. That m we have to replace by this m0 upon this one. So we will get this equation 1. Now E equal to mc square. So that is equal to m0 c square upon under root 1 minus v square by c square. So exactly calculated in the previous example, by taking E equal to 20 MeV, we have to calculate V. And we will come to 9997 into C. Then substitute this particular value of V in our equation. Okay. So R, that is equal to V upon B into E by M, right? And then solve it, you will get the answer. Okay. એમની આ બધી જ વેલ્યુઝ જો અહીંયા આપણી પાસે છે E by M0 1.76 into 10⁻11 અને આ જે પોર્શન છે ને એ ઓલરેડી અહીંયા આપણે એકવાર કેલ્ક્યુલેટ કર્યો છે, ડાયરેક્ટ એને સબસ્ટિટ્યુટ કરી દેવાનો. ઓકે, so we will get the answer. Clear to all of you?
સર ડેમી પાછળ કરો ને.
11.22. An electron gun with its collector at a potential of 100 volt fires out electrons in a spherical bulb containing hydrogen gas at low pressure of the order of 10⁻²⁻2 millimeter of Hg. A magnetic field of 2.83 into 10⁻²⁻2 Tesla curves the path of the electron in a circular orbit of radius 12 centimeter. Determine E by M from the data. So the accelerating voltage, that is 100 volt, B, that is 2.83 into 10⁻⁻4 Tesla, radius of the circular path, that is 12 centimeter, so 0.12 meter. We have to calculate E by M. Okay. So when electron is accelerated with 100 volt, the kinetic energy gained half mv square, that is EV. Okay. Then when it is subjected to the magnetic field B, the required centripetal force mv square by r, that is provided by the magnetic force EVB. So one V will be cancelled. So make V as a subject. So V equal to EBR by M. Now substitute this particular equation of V obtained here in this previous equation. So half M V square. So E square, B square, R square upon M square we can write on right hand side EV as it is. Okay. From both the side, one E cancelled. Here on left hand side, one M cancelled. So now make E by M as a subject. So E by M equal to 2V upon B square R square. So 2V given to you, that is 100. B, that is also given to you, and R is given to you. So substitute all the values, then solve it. You will get E by M. Clear? 11.23. A. An X-ray tube produces a continuous spectrum of radiation with its short wavelength and at 0.45 angstrom. What is the maximum energy of a photon in the radiation? B. From your answer to A, guess what order of accelerating voltage for electron is required in such a tube. Lambda given to you, that is 0.45 angstrom. અહીંયા R print થઈ ગયો છે, એ સુધારી નાખજો તમે. So that is 0.45 into 10⁻⁻10 meter. H is always given to you. C always given to you. Now maximum energy of the photon E, that is hc by lambda. Substitute all the values of h, c and lambda, then solve it. Then we will get the final result, that is 25.8 keV. Then see here, what order of the accelerating voltage is required. So accelerating voltage required, that should be greater than the energy of the photon. It implies that here energy, that is equal to 25.8 keV. So the voltage required, that is 25.8 kV. Clear? 11.24. In an accelerator experiment on high energy collisions of electron with positron, a certain event is interpreted as annihilation of an electron-positron pair of total energy 10.2 billion electron volt into 2 gamma rays of equal energy. What is the wavelength associated with each gamma ray? Now see here, in this annihilation process of electron and positron, total energy that is 10.2 BeV, and that is associated with 2 gamma rays which are produced in this one. So energy of each gamma ray, that is half than this one. So half of 10.2, that is 5.1 BeV. So B, that is 10 raised to 9 into EV. So energy, that is 5.1 into 10 raised to 9 into 1.6 into 10 raised to minus 19, this much joule. Now we want to calculate lambda. So energy E, that is hc by lambda. So lambda, that is hc by E. Now here substitute the values of hc and energy, this one, and then solve it. You will get wavelength lambda associated with the gamma rays. Clear? 11.25. Estimate the following two numbers. Should be interesting. The first number will tell you why radio engineers do not need to worry much about photons. The second number tells you why our eye can never count photons, even in barely detectable light. A. The number of photons emitted per second by a medium wave transmitter of 10 kilowatt power, emitting radio waves of wavelength 500 meter. B. The number of photons entering the pupil of eye per second corresponding to the minimum intensity of white light that we humans can perceive, that is nearly 10 is to 10 watt per meter square, here per meter square. Okay. Take the area of the pupil be about 0.4 centimeter square and the average frequency of white light, that is 6 into 10 is to 14 hertz. Okay. Now see, energy transmitted per second means after all that is power. 10 kilowatt, so 10 raised to 4 watt with wavelength lambda 500 meter. So energy of one photon, that is hc by lambda, substitute the value of hc and lambda, you will get this much energy. Now number of photons emitted per second, that is power upon energy of each photon. So power, that is 10 raised to 4, energy of each photon which we calculated, substitute here, then solve it. You will get the number of photons emitted per second. Tremendous large one, unbelievable. Okay. Then B. Now intensity of light, that is 10 raised to minus 10 watt per meter square. Here this intensity means amount of energy incidenting per unit area per unit time. Okay. So this one is the energy incidenting per unit area per unit time. The area of the pupil that is given to you 0.4 centimeter square, that is 0.4 into 10 raised to minus 4 meter square. So here on 1 meter square 10 raised to minus 10 joule energy incident per second. Therefore on the given area how much energy incident per second? So we have to multiply it by this area. So light energy incident on human eye, that is 10 raised to minus 10 into 0.4 into 10 raised to minus 4. So you will get this much watt. This is the power. Okay. Now frequency of light that is given to you 6 into 10 raised to 14 hertz. So from that we can calculate the energy of photon, that is HF or H nu. So substitute value of H and nu, that is the energy. Now number of photons entering to eye per second, that is the power upon energy of each photon. So power, that is 0.4 into 10 raised to minus 14, here we calculated, upon energy of each photon, that is this one, HF, substitute it, and we'll get the answer 10 raised to 4 per second. Clear to all of you? 11.26. Ultraviolet light of wavelength 2271 angstrom from a 100-watt mercury source irradiate a photocell made of molybdenum metal. If the stopping potential is minus 1.3 volt, estimate the work function of the metal. How would the photocell respond to high intensity 10 raised to 5 watt per meter square red light of a wavelength 6328 angstrom produced by HENE laser? Now see, initially lambda given to you, that is 2271 angstrom, that is 2271 into 10 raised to minus 10 meter. Stopping potential, that is 1.3 volt. Now we have equation EV0, that is HF minus 50. So EV0, that is HC by lambda minus 50. We want to calculate work function. So 50, that is HC by lambda minus EV0. Now all the values H, C, lambda, E and V0 are given to you. Substitute the values and solve it. You will get work function in terms of joule. Then divide it by 1.6 into 10 raised to minus 19. You will get work function in terms of electron volt. Then for red light. Now for red light, lambda, that is 6328 into 10 raised to minus 10 meter. So energy associated with it, that is Hc by lambda r. Calculate it. That will be less than 50. And if the energy incidenting is less than the work function of metal, then photocell will not respond to that particular radiation, or in other words, we can say the photoelectric effect that will not be obtained by that particular radiation. Clear? Then 11.27. Monochromatic radiation of wavelength 640.2 nanometer from a neon lamp irradiates photosensitive material made of cesium on tungsten. The stopping voltage is measured to be 0.54 volt. The source is replaced by an iron source and its 427.2 nanometer line irradiates the same photocell. Predict the new stopping voltage. Simple. For lambda 1, 640.2 into 10 raised to minus 9 meter, the stopping potential, that is 0.54 volt. Then lambda 2, 427.2 into 10 raised to minus 9 meter, we have to calculate the stopping potential. Now we have equation EV0, that is equal to HC by lambda minus 50. So here we can prepare two equations. EV01 equal to HC upon lambda 1 minus 50. Second one, EV02 equal to SC by lambda 2 minus 50. Now, take the difference of these two equations. EV02 minus EV01. SC upon lambda 2 minus 50 minus HC upon lambda 1 plus 50. Then on left hand side, take E common. So V02 minus V01, that is, now on right side take SC common. So 1 upon lambda 2 minus 1 upon lambda 1. Now V02 minus V01, that is HC by E into 1 upon lambda 2 minus 1 upon lambda 1. Now make V02 as a subject. So V02, that is equal to V01 plus HC by E into 1 upon lambda 2 minus 1 upon lambda 1. Now we have all the values V01, H, C, E, lambda 1, lambda 2. Substitute all the values here on right hand side, and then after solve it, you will get the stopping potential. Clear? 11.28. A mercury lamp is convenient source for studying frequency dependence of photoelectric emission, since it gives a number of spectral lines ranging from the UV to the red end of the visible spectrum. In our experiment with rubidium photocell, the following lines from a mercury source were used. So these are the wavelengths of the light used. Okay. Then stopping potentials or stopping voltages respectively were measured to be these, and these for respective wavelengths. Then determine the value of Planck constant H, the threshold frequency and work function of the material. See here, lambda and stopping potentials are given to you. So from this one, first of all, we have to calculate the frequency of each radiation. So frequency, that is C by lambda. So as per this equation, frequency associated with this first wavelength of light, that is nu1 equal to C by lambda 1. Substitute the value of C and lambda 1, then solve it, you will get the frequency, and for that particular radiation the stopping potential is given to you this much. So exactly similar to this one, calculate the frequency for each radiation, and for each one the stopping potential is given to you. Clear? Then after, say, draw the graph of stopping potential versus frequency, because in Einstein's equation we know this thing. Stopping potential V0, that is equal to H by E into nu minus nu 0. So if we draw the graph of stopping potential versus frequency nu, then the slope of graph will give you H by E, and the intersection at frequency axis, that will give you the threshold frequency. That will give you threshold frequency. Okay. So calculate the slope of the graph, that is H by E. It will come to 4.1 into 10 raised to minus 15. Then take E on right hand side and make H as a subject. You will get value of H. Then here intersection on frequency axis, that is the threshold frequency. So here threshold frequency once you get, then work function 50, that is H nu 0. Substitute the value of H and nu 0. You will get work function in terms of joule, then divide it by 1.6 into 10 raised to minus 19. Your answer will be in terms of electron volt. Clear to all of you? The work function for the 11.29, the work function for the following metals is given. For Na 2.75 eV, K 2.30 eV, for MO 4.17 eV, for Ni 5.15 eV. Which of these metals will not give photoelectric emission for a radiation of wavelength 3330 angstrom from a HECD laser placed 1 meter away from the photocell? What happens if the laser is brought nearer and placed 50 centimeter away? Okay. Now lambda given to you, that is 3300 angstrom. અહીંયા સુધારી લેજો જરા. 3300 angstrom. Now that is 3300 into 10 raised to minus 10 meter. So energy of photon, that is E equal to Sc by lambda. Substitute the value of H, C and lambda, then solve it. Then you will get the answer in terms of joule. Divide it by 1.6 into 10 raised to minus 19. You will get energy in terms of electron volt. Now to get the photoelectric effect, the energy of incident radiation, that should be greater than the work function of the metal. Now see here, 3.76 is greater than 2.75 and 2.30. It implies that The photocell made by sodium and potassium will give you the photoelectric emission, right? Rest two photocells will not give you photoelectric emission. Then after, see here it is given to you, what happens if the laser is brought nearer and placed 50 centimeter away. If it is brought nearer or far away, then the frequency of the emitted radiation will not be changed. Frequency, that is the characteristic of source. It does not depend on the position of it. So those photocells which are not giving you photoelectric effect will not give you, because frequency remains same one. So energy, that will remain the same one. Those two photocells made by sodium and potassium will continue to give you photoelectric emission. But now for those two photocells, what happens? When the distance decreases, then intensity increases. And due to that, the photoelectric current, that will increase. Clear to all of you?